This document is an official, time-stamped prediction generated by the SYAN.EARTH platform. It forecasts environmental conditions over a 90-day window from February to May 2026, specifically predicting that the North Atlantic spring phytoplankton bloom will initiate between April 12th and 26th. The forecast relies on specific atmospheric tracking. The engine identified a negative North Atlantic oscillation phase, a weather pattern that pushes Arctic air south, coupled with a sudden stratospheric warming event that triggered a polar vortex collapse in mid-February. To visualize these intersecting events, the system relies on a V9 digital twin interface. This render features a cyan glowing Earth with rotating cloud layers and 25,000 active chlorophyll particles dynamically tracking coastal upwelling zones. Powering this visualization is an immense data architecture. It ingests 366 years of historical climate records from the Central England temperature dataset and correlates them with live satellite telemetry from NASA PACE and Sentinel-3. Building an enterprise-grade predictive engine of this complexity typically requires teams of specialized software engineers and climate scientists. This platform was engineered by a single, non-technical founder using a proprietary AI orchestration pipeline. Individual founders can now bypass traditional technical roadmaps. By using orchestrated AI, a single person can deploy complex, non-linear ecological models that rival institutional platforms. When correlating 17th century historical weather observations with modern bioargo ocean float data, systems frequently suffer from semantic interoperability failures. This occurs when disparate data systems cannot accurately interpret the meaning of each other's data, resulting in corrupted analysis. Traditional passive databases fail under this workload. They rely on manual polling, which introduces latency, and their legacy code requires a rigid stop, modify, restart lifecycle for every logic update. Solving this requires a nomological state space. A nomological state space is a mathematically rigorous framework that defines the exact set of physical and environmental states that are scientifically possible within a given domain. Predicting nonlinear ecological failures requires a shift from passive data silos to an active system, one that autonomously monitors its own state and reacts to environmental triggers in real time. To build this system, the founder deployed a multi-LLM retrieval augmented generation, or RAG, pipeline. A RAG pipeline enhances a language model's responses by retrieving facts from a specific external knowledge base before generating its output. This diagram illustrates the blueprint for the SYAN.EARTH orchestration layer. It maps the flow of information through a unified intelligence system designed to bypass traditional coding. Looking at the input layer, raw data is ingested from voice transcripts, text documents, and structured knowledge. This feeds into a repository of over 70 distinct notebooks. The processing burden is handled in the center. Make.com acts as the orchestrator, coordinating between Gemini Ultra and Vertex AI to synthesize and structure that knowledge base. This architecture powers an automated feedback loop: execute, fail, adjust, repeat. The pipeline tests its own outputs and refines them until the logic holds. The result of this loop is thousands of lines of Three.js and React code found in the platform's deployment logs. This code successfully executes the exact rendering logic required for the photorealistic Earth, turning raw data into a living, breathing digital twin. This orchestration pipeline translates elite academic theory directly into deployed code, stripping away traditional development bottlenecks. The mechanical foundation of this autonomy is the Event Condition Action, or ECA, paradigm. It operates as the central nervous system of the platform, defining how the software perceives, filters, and reacts to incoming data. Early active systems built in C++ were limited by rigid memory management and required full system restarts to update logic. Shifting to a dynamic Java-based engine allows operators to hot swap monitoring rules at runtime, maintaining continuous 24/7 uptime. This diagram contrasts standard database monitoring with an active ECA engine. Instead of a passive polling cycle, the active system uses a Snoop-based event graph to fire a direct response the millisecond a threshold is breached. The event graph is a hierarchy. At the bottom, leaf nodes capture primitive events. Those signals flow upward into composite operators, using logic gates to recognize complex, time-sensitive patterns. To prevent the graph from being overwhelmed by high-frequency telemetry streams, it utilizes the four-number rule. This is a short-circuiting mechanism that performs an instant check to prune irrelevant events before they propagate up the tree. When a relevant event reaches the top of the graph, the system uses a Fessy bridge. The Fessy bridge evaluates logical conditions as text strings at runtime, allowing administrators to adjust thresholds without touching the core codebase. This architecture provides the active business intelligence required to initiate responses the moment an ecological shift is detected. High reactivity is dangerous if the underlying data concepts are flawed. To prevent AI hallucinations in scientific modeling, data governance must operate at the strict ontological level, distinct from standard logical structuring. Consider the apple versus red dilemma. In neutral systems, the physical entity apple and the contingent property red get the same structural weight. The unified foundational ontology corrects this. Apple becomes a rigid kind, defining identity, while red is just a temporary attribution. To guarantee the language maps truthfully to reality, the model is evaluated for soundness, ensuring total system completeness, maintaining absolute structural lucidity, and strict data laconicity. If a single primitive represents multiple real-world concepts, the model creates dangerous ambiguity. The system enforces rigidity. These are properties essential to an entity's existence, ensuring the database maintains identity integrity even as objects change states over time. These rigid definitions form the nomological state space. Because the laws of physical reality are hard-coded into the data structure, the engine is prevented from representing ontologically impossible facts. This ontological rigor acts as a precise filter. It ensures that the correlations identified by the AI are grounded in physical reality, rather than just statistical probability. The synthesis of these systems produces actionable intelligence. The ECA engine tracks a sudden stratospheric warming event in real time and pairs it with 366 years of historical winter severity patterns from the HAD-CET records. This chart shows the causal chain calculated by the engine. The stratospheric warming event leads to an extended mixed layer depth in the ocean. This prolonged mixing loads the surface with nutrients, which directly leads to an elevated probability for harmful algal blooms. Applying this logic, the system generated its formal prediction for the Florida West Coast. It identified a risk for red tide blooms initiated by the convergence of rapid spring warming and a transition to an ENSO neutral phase. The prediction document details these correlation chains, established by precise R values linking winter cold fronts to the exact timing of the spring bloom onset. Reacting to an algae bloom after it occurs results in millions of dollars in losses. An automated 90-day predictive alert provides the lead time necessary to deploy evasive logistics before the damage is done. The competitive advantage of SYAN.EARTH is its ability to identify atmospheric precursor patterns months in advance, patterns that are often invisible to standard short-term operational forecast models. The technical barrier to building complex predictive engines has dissolved. Orchestrated AI pipelines allow a single operator to translate theories into functional, enterprise-scale software. SYAN.EARTH serves as a proof of concept for a development model where the primary constraint is not technical skill, but the conceptual clarity of the underlying model.